Dear students, today our topic is about vibrational energy levels. Vibrational energy levels in a molecule. When molecule is sufficiently excited, then it can vibrate as well as it can rotate. So it has the vibrational energy level and it has the rotational energy level. So today we will talk about the vibrational energy. When the molecule vibrate, it has the vibration energy and vibrational energy levels. So here we will consider diatomic molecules, that is atom consists of two atoms of mass m1 and mass another atom of mass m2. So when they are in equilibrium positions, then the distance between them is the r naught. So here we will consider the two atoms just like the two masses of mass m1 and m2 attached by a spring, tied by any spring. Like we can say that these are like m1 tied with the mass m2 by spring. So when they are in equilibrium position, their separation between them is the r naught. So as spring is the elastic in nature, here we consider the diatomic molecules like perfectly elastic, so we can stretch them. When we stretch the spring, then we can increase the distance between them. Like now the situation is like this, so we can increase the distance and this distance can be represented by r. Now we can apply the Hooke law. As you know that we can apply the Hooke law to the bodies which are attached with the spring. So according to the Hooke law, restoring force is directly proportional to the displacement. So here the restoring force, we can say that is directly proportional to r minus r naught. That is, when we stretch the spring, we increase the displacement. So it's directly proportional to this one, displacement. When we remove the proportionality sign, we can write it like F is equal to minus K into R minus R naught. We can also write it like F is equal to minus Kx. That is, X is equal to R minus R naught and K is the proportionality constant. So here we will use another concept, that is the concept of reduced mass. That is, instead of two atoms of mass m1 and m2, here we will consider a single mass m that is connected with the spring, and just like the single mass, and this mass can be either represented by m prime or m bar, or either it can be represented by mu. So mu is equal to m1 m2 divided by m1 plus m2. So this one is the equation of Hooke law, and this is one is the equation number 1. Now according to the Newton's second law of the motion, according to the Newton's second law of the motion, F is equal to ma, and we can write, instead of m here we can use the reduced mass mu, and a is equal to d square x divided by d square. So this one is equation number 2. Now we have the two equations of the force. One equation from the Hooke law and another equation from the Newton's second law. And here you can see that Now the situation is like the simple harmonic motion, that is, this mass m moves about the mean position just like the simple harmonic oscillator. So we will consider the diatomic molecules like the simple harmonic oscillator, and we will solve the equation of simple harmonic oscillator for diatomic molecule. So now we have the two equations. One equation from the Hooke law, that is F is equal to minus kx. This one is our equation number 1, and another equation of force from the Newton second law of the motion, that is F is equal to mu d square x divided by d square. This one is our equation number 2. Now both are the equations of the force. Now we can equate both these equations. Now by equating the equation 1 and 2, so this will be equal to the mu d square x divided by d square will be equal to minus kx. So we can also write it like the mu d square x divided by dt square plus kx will be equal to 0, or either we can write it like the d square x divided by dt square plus 1 over mu into kx will be equal to 0. This is now we can replace the k divided by mu with, we can write it like the d square x divided by d square plus we'll write it like the plus omega square x is equal to 0, as omega square is equal to k divided by mu. Here k is the angular velocity. So this one is the differential equation, second order differential equation for simple harmonic oscillator. It is simple harmonic oscillator. So as the angular frequency, we can write the angular frequency like omega is equal to k divided by mu under root. That is the angular frequency of the simple harmonic oscillator, and angular velocity, and we can write the angular frequency like 2 pi mu naught is equal to k divided by mu. That is, this one is the very well known relation for the equation for the frequency of simple harmonic oscillator. We can write it like mu naught is equal to 1 by mu into k divided by mu. This is the frequency of simple harmonic oscillator. That is frequency. We can also say that this one is the frequency of vibrating molecules. So in our next part of our this video of vibrational energy level, we will solve this differential equation for the simple harmonic oscillator. So for more information about this topic, please watch our next video, that is the second part of this video. Thank you so much.